So we're going to talk about the big ball of mud. And I'm pretty sure that most of the people who had worked in the software industry for some time understand the concept of a big ball of mud, because that's what most people are actually working with. I also know that most people are not too happy to work on a big ball of mud. It's not always fun. It's actually sometimes very dangerous and very dangerous to make changes, because it's hard to basically understand the consequences of those changes, because big balls of mud are suffering from high coupling and other issues. We're going to go into details. First, we're going to talk about what is a big ball of mud. And we're going to look at a very nice example, open source project called Apache Cassandra. Then we're going to discuss the characteristics of big balls of mud. And then we're going to find out how can we detect it if our project turns into a big ball of mud, and how can we stop it at the end from happening in the first place. And what are we going to do if we already have a big ball of mud. So this is a screenshot of a dependency diagram. I think we can agree that it looks a little bit like a ball. We see something like 1,553 Java files that form one big cycle. It means from each of those 1,500 Java files, you can reach any other one and come back another way. So basically, they form one gigantic big Java file, one logical big Java file that comprises basically most of Apache Cassandra, which means that the original architecture has been lost or simplified to the maximum, because in that case, you could say it's a simple architecture diagram with one box labeled Apache Cassandra, no further subdivision. So I'm pretty sure the original developers still understand their code base a little bit, but we also could agree that somebody who comes from the outside and needs to do meaningful changes to this code base might have a hard time doing that. So what happened here? So I'm trying to prove that once a project becomes a big ball of mud, it will be very difficult to come back from it. And what I did an analysis of different open source projects, and one of them was Apache Cassandra. And here what I did, I compared 5 different versions of Apache Cassandra, started with version 1.0 up to version 4.1. And I think now we have even a newer version that has even worse characteristics than the previous ones. So what we can see in a trend, which I'm able to prove also with many other projects, once you get those big cycle groups in a system, they tend to grow. That's why I call them code cancer. They're like little tumors, and as soon as they grow over a certain size, they will develop some dynamic growth that at the end will eat up your whole system. And as I said, by just looking at the data, we can confirm that things got worse with every new version. They are caused by growing groups of elements involved in cyclic dependencies. And once you have one of those bigger cycles, let's assume you have 20, 30, 40 classes in a cycle, it's very easy to add new classes to that cycle without even knowing it. Because they're already, the bigger those cycles become, the more they develop their own kind of gravity and attracting more and more dependencies from the outside, which at the end only means that the cycles are growing. So this is how it started, how it's going. So version 1.0, we had 296 classes in a big cycle, already pretty big. And now in version 4.1, we have 1,553. So the two graphs, of course, because most of the files are not visible on the right side, the right one doesn't look so much worse than the first one. So the first one was already pretty bad. But now we are in a stage where it becomes very, very difficult to put any structure in this, any architecture structure on top of Apache Cassandra, because everything is literally connected to everything. By the way, the different colors in the graph are forming different parent packages. So each of those little rectangles is one Java file, and all Java files with the same color are in the same package. So here we have different charts where we compare those numbers over time. So we can see in the first chart on the top left that the lines of code from version 1 to version 4.1 grew from about 50,000 lines of code to over 300,000 lines of code. The number of Java files went from 500 to 2,200 or something like this. And then the number of packages went from 40 to over 120. Now we have two metrics here called propagation cost and maintainability level. Blue is propagation cost. Propagation cost means if you have a propagation cost value of 70%, it means if you change a random file, if you're in your system, 70% of the system will be affected by that change. And that's quite a big number. Then maintainability level is a metric that we developed together with some of our customers, where we look at how maintainable is a module in your software. So it's computed on the module level, and it takes into consideration the dependency structure, the amount or size of cycle groups, and similar things. The best value is 100%, the worst value is 0, and you can see it's pretty close to 0. So it started in version 1 a little bit over 20%, and then after that it fell to the 10% range and never really recovered from that. Propagation cost at the end is brutally high, almost 80%. So every time I change a file in Apache Cassandra, 80% of the Apache Cassandra code base might be affected by that change. So that, of course, dramatically increases the chances of regression bugs coming in. It also makes it much harder to test the code because you cannot test anything in isolation. Never even talking about how would you be able to understand that code base if there's so much coupling and everything is kind of related to everything else. We can also see that the number of elements in the biggest cycle group is continuously increasing. From version 1, it was 296 to 1553. So that's a pretty steep increase. Also, the biggest package cycle groups went from about 30 to 110 packages. And relative cyclicity is another metric, which I will explain down the road in this presentation. Also went up to the 90% range on the package level and to the 70 to 80% range in the Java file level. So that is what I'm trying to prove here. Once you have this kind of code cancer, it usually only gets worse. That's why it makes sense to think about why is it happening in the first place and what can we do to stop it. After all, Cassandra is quite a successful project. It's used in many production environments and a very popular open source project. But it has no discernible architecture. It is hard to understand, especially if you're new to the project, because then you have to basically read the whole code base to have an understanding how everything works. It is basically impossible to test anything in isolation. It has no modularity whatsoever. And it's just one big jar of highly coupled code, which means you also have a higher risk of vulnerabilities. Just imagine you want to harden that code base against cyber threats. The more complicated the code base is, the more highly coupled it is, the more difficult it will become to harden the code base against threats from the outside. Yeah, and of course, we already talked about the chance of regression bugs. The probability increases dramatically because every time we change a file, about 1,500 files are directly or indirectly affected by that change due to the extremely high coupling values in that project. So, another argument is that big ball of muds, BBOMs, are expensive. Very expensive indeed. Just in the United States, there was a report from CISQ about the total cost of poor software quality, and it is estimated for 2020 that this cost was in the range of $2 trillion, which is roughly 10% of GDP, quite a bit of money. And there's a new report out in the meantime from 22 that has even worse numbers in there. So we can assume that poor software quality costs a lot of money over time. We have a relatively large bubble of unsuccessful IT projects, 260 billion alone. That is a little shocking, right? Because we're developing software for more than 50 years now. You would hope that we figured out how to do it right in the meantime, but obviously not. We're still having issues finishing projects successfully, obviously. We have legacy systems with 520 billion, operational failures with 1.56 trillion, which is quite a big number. And there are many famous examples of bad software quality. Let's talk about Boeing 737 MAX, for example. It's a nice example where sloppy software development and sloppy quality control actually led to the death of 400 people. And totally destroyed the reputation of Boeing, and they're still trying to recover from it. And obviously, if you read the news, those problems are not totally solved at Boeing yet. If the doors can fly out mid-flight, that's a serious quality issue too. But it's all related. So the quality of the airplane, the software, all is related together. And there are many other examples where poor software quality at the end cost real money. Now, why? There are some more interesting findings in this report. For example, failed projects are up 46% from 2018. And I was wondering why that happened, but I think there's a relationship between the hype going to microservices, which started in about 2015. There are many organizations switched to a microservice architecture without really knowing what they were doing. So many of those microservice projects actually failed, and I've seen a couple of them because we also do software assessment services, and I can tell you there are lots of issues. Microservices are not a bad thing in itself, but it requires a more skilled team to write a microservice compared to a monolith, and it also puts a lot of burden on your end users because now they have to manage many services that have to kind of be orchestrated, running in a Kubernetes cluster or something like this, and all that increases complexity. It also increases programming complexity because as soon as one microservice has to talk to another one, you need some inter-process communication mechanisms like message queues and similar things, which increase complexity and do not decrease complexity. What are the key recommendations from the report? One of them says, ensure early and regular analysis of source code to detect violations, weaknesses, and vulnerabilities. That is where you actually need tools. And very few people use tools for that. We're going to talk about some tools a little bit down the road here. Then measure structural quality characteristics. I couldn't agree more. That's why we have a tool called Sonograph that can do all those things. And there's even a free version of it called Sonograph Explorer, which you can basically download for free from our website, hellotomorrow.com, and use for free even in commercial context. And it will compute most of those metrics for you and give you some basic information about cycles and similar things. There's also a commercial version of the product that can do nice visualization and other stuff if you wanted to have a little bit more than just the basic features. Yeah, and then recognize the inherent difficulties of developing software and use effective tools to help with those, to deal with those difficulties. Again, a totally correct answer, but very few companies actually do something about that. And I can kind of relate very well with that, because when I go to conferences, I often ask, I talk about this topic very often, so I often ask, how many of you having a formally defined architecture model for the project they're working on right now? And less than half of the hands go up. Most people don't have a formal architecture. It's something that is maybe communicated verbally or hidden in some documents, but it's not a lot. So there are basically some basic rules, what you should do and what you shouldn't do, but it's not enforced in any way, shape, or form. Of course, now it's much easier for the big ball of mud to grow, because if there are no boundaries, no rules that are enforced when it comes to the dependency structure, those issues can happen very easily. So you need tool basically to figure out what's going on with your code base. And you need rules, enforceable rules, ideally something that breaks your build when something is happening that is not supporting your current architecture. Now let's talk about how can we, what are the characteristics of a big ball of mud and how can we measure that? So a big ball of mud have few but large groups of cyclic elements. So that's the sign of end-stage code cancer. If you have those big cycle groups, few big cycle groups. In Apache Cassandra, there was one big cycle group, and now it metastasized to a second one with only about 100 elements. But if you have few large cycle groups, then you have a big ball of mud. Once they grow over a certain size, they basically are like black holes in the universe. They develop a lot of gravitational pull and pulling more and more components into their orbit. And of course, we have some metrics, which I'm going to explain in the next section, that allow you to detect this problem early on. And the first good strategy to fight the big ball of mud is monitor cyclic dependencies and not allowing to let those large cycle groups grow. That would be a first strategy, at least to stop the bleeding. And of course, if you can do that, an enforceable architectural model is even better. Why is an architectural model better? Because in an architectural model, you actually talk about the structure of your code base. And I'm a big fan of domain-driven design. Basically, you cut your system by functionality first, and then you have those different domains. They should have a cycle-free dependency structure between them. And then inside the domains, you can have layering, like a UI layer, a controller layer, a service layer, persistence layer, and so on. And then once you have this enforceable structure, you will know which dependencies in your code base have to go anyway because they violate the structure. And many times, removing those unwanted dependencies leads to less cycles and better structure. But of course, without using proper tools, fighting this problem becomes very, very difficult. So why does it happen so often? Because I'm pretty sure if I could see you now and I would ask you, do you like working on a big ball of mud? Very few hands would rise up. And if I ask you, do you intentionally create a big ball of mud? Nobody would agree to that because we're not doing that intentionally. We're not trying to create the worst possible software structure that we can. I think most developers I know are striving to create good code. It is much more fun to work on a good code base. Anyway, as soon as we have enough people working on the same code base, that is the usual outcome. So you need to put active countermeasures in place. Otherwise, a big ball of mud is the default outcome for any non-trivial project. And I've proven that a million times. I've done so many software assessments. I can tell you that 80% of non-trivial systems are ending up as a big ball of mud. It's our default architecture design pattern. So another reason, because we have no formal definition of our architectural model. And even if we have it, we lack an enforcement mechanism because it's nice to have your architecture on paper, but the paper won't tell you if your code base is conforming to the architecture. So without proper tools and dependency visualization, those structural issues are introduced without the developers being aware of the problem. They're not doing that intentionally. Developers are not stupid, but it's really hard if you're working on a big code base with thousands of files to understand all the dependency implications of the changes you are doing without some tools that help you visualize that. And as I said, as the cycle groups are growing like little tumors, so they create a snowballing effect until your whole code base is affected. And also, it's not easy to communicating architectural rules. That's why a formal description that is enforced by a tool can be so helpful, because then there's no interpretation of the rules possible, because the tool decides what is right and what is wrong. And of course, we're always working under time pressure, and time pressure encourages shortcuts, definitely. So many times we're just pragmatic and skip over a couple hoops just to make sure that we are faster and that we meet our deadline. And at the end, we create increased technical debt by that. But usually we don't have the time after the deadline to fix the technical debt that we already accumulated. And if you never fix or address your technical debt, it just only grows and makes things harder and harder until you reach a point where every change becomes increasingly very, very difficult. So some people said, oh, microservices to the rescue, right? So just make smaller code bases and then everything becomes easy. Of course, the major cause for the big ball of mud is that it's hard to define and enforce architectural boundaries. But that problem does not go away by simply splitting it up into a monolith into many smaller services, because you still have the dependencies between those services. So basically what many people do when they jump blindly into microservices architectures, they basically split up their big ball of mud into a distributed big ball of mud, which is even worse than what we had before. Of course, there are many good cases for microservices, but they're not the silver bullet. And the author of this famous book about microservices, Sam Newman, wrote it very nicely. You have to convince me that I need microservices, and you have to have good arguments for it, because the default architectural pattern should still be the monolith. The monolith is a valid architectural pattern. The fact that so many people have problems with monoliths is due to the fact that very few people are able to basically create a nicely structured monolith, because they have no tools to enforce architectural rules. If you have a well-structured monolith, we also call those moduliths for modular monolith, then you don't have the usual problems that you normally have with monoliths. And the argument that you need microservices for scaling or scalability is not always true. Sometimes it is true. Sometimes you can just split your big monoliths into two services and already create something like great improvement in scalability. Sometimes scalability is not improved by just splitting a service up into a smaller one. It depends on the architecture characteristics of the different services you're creating. But using microservices just by itself creates more problems than you used to have before. There can be a good solution, but not everybody is Netflix. Not everybody needs Netflix scalability. And not everybody has a rockstar developer team that the people at Netflix have, that obviously understand all these complex things and complex relationships and can make it work. So microservices can be a good solution, but they increase overall complexity. They do not decrease it, they increase it. And we know by now that many of those microservice migration projects actually fail. Because as soon as you get into the details and the nitty-gritty, things can get very nasty very quickly. So we talked a lot about why it's happening and what the big ball of mud is. Now it would be useful if we could actually get some metrics that help us finding out what is wrong with our software, and maybe detect harmful trends early by using a metric-based feedback loop. So two metrics I'm going to explain pretty quickly is average component dependency and propagation cost. Those two are related. Then we're going to talk about what are cycle groups. We're going to introduce some cycle analysis metrics. And we're going to talk about that metric maintainability level, which we developed together with some of our customers. Let's start with average component dependency. That's a simple metric. On the left side, so we have a couple dependency graphs here. The boxes are source files, the arrows are dependencies between those source files, and the numbers are the so-called depends upon values. On the bottom, the depends upon value is 1 because this file only depends on itself. This one depends on this one, and on itself. That's why we have a 3 in there. And this one depends on all the other ones directly and indirectly plus itself. So that's why we have a 6 in there. If we add up those numbers, we get cumulated component dependency. 6 plus 3 plus 3 plus 3 times 1 gives you 15. And if we divide it through the number of boxes, we get average component dependency of 2.5. Means in that dependency graph, every file on average depends on 2.5 files, including itself. Now in the middle, we see what happens if we apply the dependency inversion principle. That means it allows us to turn around to the direction of dependencies. So in that case, the 2 files in the middle become the bottom of our system. And we get a better value of 2 instead of 2.5. Minimum value would be 1, which means we have 6 islands with no connection between each other. Maximum value would be 6. Means everybody's literally connected to everybody. And here we see what happens if you just add one dependency that would create 2 cycles, one to the left, one to the right. and then we get a much worse value from 4.33, which is pretty close to the maximum of 6. So cyclic dependencies are always making average component dependency worse. Now, the input metric for average component dependency is depends upon value. Yeah. So we just explained depends upon. This is a graph of the same thing. This only depends on itself. This one only depends on this and on itself, and so on. That's how you get the numbers. There's a mirror metric used from, which just turns the question around, said how many people are using me directly or indirectly, and then the one on the bottom gets the biggest number, and the smallest numbers are on the top here because it's only used by themselves. The funny thing is, and necessary by mathematics and graph theoretical reasons, if you add up the depends upon values and the used from values from the same graph, you always get to the same number. In our case, it would be 3 plus 3 is 6, 12, 14. And here we also have 14, if you add it up quickly. So same number. And then we can normalize those numbers, divide by the number of boxes, which gives us a metric fan out or fan in here. Propagation cost is basically the percentage value to indicate coupling. We learned that Apache Cassandra had about 70% propagation cost. And we can calculate that very easily by either taking the average value of fan in or the average value of fan out. Or we can divide average component dependency by the number of components. Once more, gives us the same value. All result in the same number, which is a percentage value, which tells us how strong the coupling in our system is. Yeah, as soon as you get values above 20%, you have bad values except for small systems. So propagation cost calculations make sense for larger systems. If you have very small system with 20 or 30 files, it's not really relevant because then you will get naturally high coupling values anyway because the number of files is so small. And since it's a dependency, basically a dependency percentage metric, by just adding new files to a system, this value will grow, will shrink. The value will shrink because you have more and more files, so the density of relationships between files compared to the total number of files will sink. It's owed to the fact that basically you have a quadratic number of dependencies. So if you have 10 files, you can have 100 different dependencies, 10 times 10. If you have 100 files, you already have 10,000 potential dependencies and so on. So the number of potential dependencies increases with the square number of nodes in your system. And so that usually, if you're not catastrophically bad at what you're doing, just adding files will let the value shrink a little bit. But still, higher values of propagation costs are always bad news. Never let it grow to the values that you see in Apache Cassandra. Now, we talked about cycle groups a little bit. Here's a visualization what that exactly means. So in this graph, we have two cycle groups, the gray one and the red one. And the white nodes are not involved in any cycles. And with Apache Cassandra before, we saw that giant cycle with 1553 elements. You can imagine that this looks a lot more complicated. No. So more about cycle groups. So dependencies can be analyzed between compilation units, packages or namespaces, or arbitrary elements defined in your code. Yeah? So I can just make a source file based cycle analysis. I take all the C# files or Java files from my system and find out if there are cycles between each other. Or I can do that analysis by just making a namespace or package dependency graph and do an analysis on this level. Or I could basically do an analysis based on directories or something like this. The different levels of cycles I can calculate, but the most popular levels I can calculate cycle dependencies between are either compilation units themselves or packages or namespaces. So in our case, we're mostly interested in compilation unit cycles and package level cycles. And smaller cycle groups with 5 elements or less within a package or namespace are usually not too problematic. So you can have smaller cycles. Some design patterns basically imply cyclic dependencies between different classes. but keep those cycle groups small. Less than 5 elements is a good idea, less than 3 elements is even better. Try to avoid package and namespace cycles at all. So if you have cycles, try to isolate the cycles within a namespace or package. But as soon as you get to the package and namespace level, it's always a good idea to keep that structure completely cycle-free. Because then you can also use your package and namespace structure to basically connect it to your architecture in some way. For example, it's a very good idea. For example, if you think about domain-driven design, you can have your namespace naming strategy. You say start with your company name, Hello Tomorrow, then the project name, Project X, and then the name of the domain, and then the name of the layer. So by just looking at a package or namespace name, you would know where you are in your architecture. The good news, all cycles can be broken. The bad news is most people don't learn how to do that. So that's something that you probably need to teach your developers in some kind of boot camp situation, or send them to some good architecture training so that they learn how to do that. I give you an example. So dependency inversion principle is a very famous way to break cycles. So that's a simple cycle between two classes. Class A and class B are using each other. And by just introducing an interface, I can break that cycle. So instead of class A pointing to B directly, it points to interface for B. That interface is implemented by B. And now we have a cycle-free dependency graph. That's why it's called dependency inversion principles. Interfaces are really good for inversing directions of dependencies. Another cycle breakup technique could be reorganization of your code. For example, we have, that's a classic example here. We have a customer class and an order class. The order knows its customer, and the customer is a convenience function. Find the order with number ID that belongs to me. Of course, the correct ordering would be that this find order function should belong to the order class and not to the customer class, and then you again get a cycle-free structure. There are other techniques too, like promoting and demoting dependencies up and down. So for example, if you have two classes that use each other, you can basically have a class above them that knows those two classes and basically internalize the cycle into its inner structure. Or you can do this with a class that is known by both of the classes in the cycle and basically demote it to the lower class. Now let's look at some cycle analysis metrics. So let's start with cyclicity and relative cyclicity. Biggest cycle group is also a good indicator. It's just a very simple metric, tells you how many elements are in the biggest cycle group. Structural depth index is a metric that tells us how difficult would it be to break all these cycles up. And let's start with cyclicity here. Cyclicity is a very simple metric. If you have a cycle group of 3 elements, its cyclicity is 9. If you have a cycle group of 10 elements, its cyclicity is 100. So it's a square number of its size. Very simple. Now we can add up the cyclicity for all cycles inside a module or inside of the whole system, and then you get a sum of cyclicity. And then you can basically calculate relative cyclicity for that container, which can be the module or the whole system, or it could even be a package, as sum of cyclicity, the square root of the sum of cyclicity divided by the number of elements multiplied by 100. So why is this metric useful, you might think? I can give you an example. Now let's make a little thought experiment here. Please follow me in your head. Let's assume we have a system with 100 source files. And the first one is using the second one is using the third one, and so on until we get to number 100, which is again using the first one. So in our head, we should have a big cycle having 100 nodes. In that case, relative cyclicity could be calculated as the sum of cyclicity. In this case, we only have one cycle of 100 elements. The cyclicity would be 10,000. The square root of 10,000 would be 100, divided by 100 would be 1. And then we get 100% relative cyclicity. So that's a worst case scenario. One big cycle comprising all elements, and we get the worst value of relative cyclicity. Now let's assume we have the same system, but instead of having one big cycle, we have 50 small cycles of 2 elements. Now if we do that exercise again, the small cycles have a cyclicity of 4, 2 times 2, times 50 is 200. The square root of 200 would be 14. So in that case, our relative cyclicity would only be 14%. Although in both cases, 100% of all source files are involved in some kind of cycle, but in the first case, it was a much bigger cycle. Basically, this metric tells us how bad is it. So if you have lots of smaller cycles, that's always better than having one big cycle. And that can be measured very nicely with relative cyclicity. That's why this metric is useful. Structural depth index is kind of the other side of the coin. There we try to answer the question, how difficult would it be to break up a cycle? And so we run a graph algorithm over the cycle groups. And for each cycle group, we compute two values. First of all, we find out how many links to have to cut to break the cycle group. And then for each link, we look at the weight of the link. So if you have a dependency between class A and class B, and class A is using class B in 3 different ways, then the weight of that link would be 3. If that's the only link we had to cut, our structural depth index value would be 13, because we calculate structural depth index as 10 times the links to break plus total weight of links. So in our example, if we had this one link with 3 dependencies, and that's the one that has to go, the structural depth index value would be 13. And of course, we then add this up for the whole module or the whole system. For each cycle group, we get a value, and then we're adding up these values for different scopes. Of course, that's a value you might want to track and then make sure that it's not growing. Because if this value is growing all the time, it means your cycles are getting denser and denser and harder to break up. Now, maintainability level is a way more complicated metric. We implemented that together with the customer. The idea was basically that's a metric we calculate per module. And for each module, we wanted to get a value between 0 and 100%. 100% would be perfect, 0% would be very bad. That basically correlates to the stomach feeling of developers about the quality of modules. And we let different inputs go into this metric. It should be stable when there are no major changes to the architecture or dependency structure. And it measures decoupling and successful verticalization. What is verticalization? Verticalization is domain-driven design. Basically, you first divide your system vertically by organizing it into different domains. And the dependencies between the domains should be minimized. So you have a successful verticalization if you can clearly see those domains in your code structure and they don't have too many dependencies between each other. And of course, reducing cycles and reducing coupling will improve the metric. And it's one of several indicators of design quality. Recommended value, 75% or more. Definitely you want to keep it above 50%. 75% is already pretty safe. If you can keep it at 75 or higher, that's reasonable. Now let's see how we calculate that metric. So this is a simple dependency graph again up there with 12 compilation units. And we calculate first of all the fan-in value maintainability level, fan-in MLL. That's a percentage of higher level components influenced by a given component. Now, if you create this graph, you see we levelize this graph. Level 1 has no outgoing dependencies. Level 2 has only incoming dependencies from higher level and outgoing dependencies to lower level and so on. But before we can levelize the graph, we need to basically condense cycle groups into their own logical nodes. So we have a little cycle group between FG and H here. So we form one logical node called FGH out of this cycle group so that we get a cycle-free graph structure. So let's calculate that fed in, for example, for node A. Yeah, A is used by E directly and by I and J indirectly. So I mean 3 nodes are using us. 3 nodes of 8 nodes in higher levels means 3 8s means a 37.5% value of fan-in ML for node A. For node E, the value is 50% because E is used by I and J, and that is 2 nodes out of 4 nodes which are in higher levels. So 50% for E. For all the nodes on level 3, we have a value of 0 because we have no incoming dependencies. Nobody's using us. So I, J, K, and L are the files that we can change without affecting the rest of the system. So that is where we should put our complicated logic. Put the complicated logic in files that have as little as possible incoming dependencies, ideally no incoming dependencies. Now you could argue, if it doesn't have any incoming dependencies and not used by anybody, so that's useless. Not true. If your class is implemented by implements an interface, you can call that interface without calling the class directly, and the class itself might have no incoming dependency, but it's still used over the interface. The interface allows you a large degree of decoupling, and as long as you don't change the interface, you can change the code in I or J as much as you want without affecting anything in the rest of your system. Now we have different calculations here. For example, fan-in of this node FGA would be 75% because it's used by J, K, and L, which is 75% of those higher level nodes. Now, there are a lot more details to this matrix because there are also alternative ways to calculate it. There's a blog article which contains all the details here. Just go to blog.hellotomorrow.com and look for the keyword promising. You'll find the article about the metric that contains all the formulas and everything in detail. Because in reality, what we found out when we developed the metric, that first step wasn't enough. So we had an example from our customer Porsche Informatik in Salzburg, Austria, where they said, we have two modules here and both of them scored in the high 90s with becoming maintainability. One module was clearly well structured. The other one was hated by most of the developers. So we tried to figure out what happened there. And it turned out that in the second module, just the structure between the compilation units was pretty nice and almost cycle-free. But the package structure was completely random and chaotic. So basically the assignment of files to packages was more or less random. There was no system in there, which means it was very hard to find the code. And that created also a lot of package cycles that were just caused by the fact that classes were in the wrong package. And that makes it hard to understand and maintain a code base. So we also added an alternative calculation, which is based on relative cyclicity on the package level. And then ML ended up to be the minimum of those two values. Once we did that, we got the desired result. The good module still scored in the 90s, while the bad module suddenly scored in the 40s and not in the 90s anymore. So developing metrics can sometimes be tricky, but once you get to a good point, I would say in the meantime, maintainability level is a pretty good metric for assessing maintainability of code modules. Now, how do you get those metrics in the first place? You need tools for that. And there's a free tool I already mentioned, Sonograph Explorer, completely free to use, also in a commercial setting. The only thing you need to do is to basically register on hellotomorrow.com and then get your free license, and you can use it, download it directly from the website and run it on your things. And maybe I'll have a little time. If I have a little time, I'm going to show you how to use it. I'm not sure. Let's see how far do we go. Short usage demo. Yeah, let's do that quickly. Yeah, unfortunately, my computer is a little slow with the software here, but I hope it will recover. Okay, now let's. So this is Sonograph here. Let's open a system here. And I'm going to go to an open source system called Gradle. Many of you are probably familiar with Gradle. Takes a little longer because that streaming software is using some part of my CPU here. Now we have the data. Still some analyzers are running. And I should soon get to my dashboard here, which gives me some overall information. So this is basically the thing that you get also with SonarGraph Explorer. You get a structure dashboard here, which tells you what structural issues you have. That looks at entangled code and cycles. And obviously we have almost 78% of the code base is entangled in some way, shape, or form. But the relative entanglement, which is based on relative cyclicity, is not as bad. So the second red bar is much smaller than the first one, which means there's still hope regarding the overall structure. You can also see that if I click down here, I can see the metric propagation cost. It's at 4.5%, so that's a good value. Average component dependency is 396. That is basically 4.5% of those 8,800 Java files that are in this system here. So I can see propagation cost here. I can see maintainability level is at near the border where I feel uncomfortable. So what I would do next is here to basically go down into the metrics view and find out which are my problematic modules. So I go here, click on module, click on maintainability level. If I can find it, no, not propagation cost, maintainability level. That's the one. I'm going to sort inversely. So we have one module called dependency management, which has a very low level of maintainability. Let's see how big that module is. I can add lines of code as a second metric. So in this case, we have 77,000 lines of code. Unfortunately, it's also our biggest module. And maybe we can also add propagation cost just for fun. Propagation cost is not too bad here in dependency management, but maintainability level is low. Let's see where it comes from. So the next step, what we usually do is look at the cycle groups. And if I look at basic compilation unit cycle groups, I see, oh man, I didn't clean up for my last demo, I'm sorry. Give me a second. It's now recalculating everything. And here we have the component cycles again. And now we see dependency management has a pretty big Java file cycle group. So this you can still get with SonarGraph Explorer with a free tool. And if I open that, I can see which files are part of that cycle. Now, if you want to see the cycle itself visualized, you would need the commercial product for that. So if I can show that in a cycle view, that it would visualize that whole thing for me in a way that you can see where's the cycle coming from. So different colors, again, represent different packages. Now, let's go back to our slides. Let's hope I can go back to presentation mode without waiting 5 minutes. Okay. Now, book recommendation. If you want to learn more about those metrics, shameless plug. I'm a co-author of this book together with 9 other people. So the book has 10 chapters. Everybody wrote his own chapter, and all the metrics I described here, plus some extra, are described in this O'Reilly book here. Now, how do we detect if a project turns into a big ball of mud? Collect metrics in your NID build and track them. That would be the first step. And check for the size of the biggest cycle group. It should be 5 or below. It becomes dangerous when it's over 30 and becomes really bad when it's over 100. Check your relative cyclicity values. Should be below 10% ideally. And as soon as it goes over 20%, it becomes dangerous. And structural depth index. How difficult would it be to break up all the cycles you have? If that metric grows over time, all the time, then it points to a problem. Which again tells me that you need a metric-based feedback loop. You need some mechanism to integrate those metric calculations into your NID build. That can be done completely free. So Sonograph Explorer also comes with a build integration. You can integrate that in your build to calculate metric reports. And then you can basically use, for example, Jenkins to display those metrics over time. Or you can use our commercial product here, Sonograph Enterprise, which is basically a metrics database where you can upload metrics on a daily basis and then see how metrics are changing over time. How do we stop the big ball of mud? By just following some golden rules. First one is define architectural boundaries. Ideally, you use a domain-specific language. It's like something that comes with Sonograph. Sonograph comes with a domain-specific language to define architectural boundaries. But you can also use tools like ArcUnit or similar. Enforce them into your CI build. Make sure that your build breaks if something is not kosher. Do not allow package or namespace cycles and keep other cycles under 6 elements. Avoid God classes. So those big classes, more than 1,000 lines of code, are usually problematic because they also have their own gravitational pull. The bigger the class, the more dependency it will attract. And also limit local complexity. Don't write those God methods that go over hundreds of lines and are very complex to understand and read. The effect of the golden rules is that your modularity will always be preserved. Coupling is minimized. That increases code readability and testability. And also you end up with fewer potential vulnerabilities. And if you do that, your system will be better off than 90% of systems with comparable size and complexity. The most important thing to remember is the developers spend most of the time reading code. We know that in most development organizations, developers spend between 80 and 90% of the time reading code and very little time actually writing code. If you want to make your developers more productive, make your code more readable, more understandable, less coupled, and then they have more time writing code. This is a little example for an ArcUnit test. So ArcUnit is an open source system where you can basically define certain rules. For example, the rule no classes that reside in a package presentation should access classes that reside in a package persistence, and so on. And that will basically break your build if that rule is broken in some way. If you use Sonograph's DSL, that looks like this. On the left side, you see the domain-specific language that comes with Sonograph. Basically, an artifact is a box in an architecture diagram. The include statement tells us what is in the box, and the connect statement tells me what it can talk to. And then here you also get a very nice description of your architecture in form of a model. That is basically UML component diagram in text form, what you see there. The main difference is that Sonograph uses a model-based approach. Basically, you create a model for your whole application. And models have a big advantage that as soon as you cover all your code with a model, everything that is not explicitly allowed is forbidden and will be found. So you can basically check for completeness of your model by making sure that your architecture covers all your code. With ArcUnit, that's a lot harder because it's just a set of independent rules that can be checked. So, and checking for completeness is difficult. But on the other hand, by all means, using ArcUnit is much better than not using ArcUnit because that allows you to define architectural boundaries. It's just not as comfortable and luxurious as what you can do with a DSL. Okay, how do we improve an existing big ball of mud? First of all, it's a good idea to find out which parts of your code base are actively worked on. There's no need of resolving cyclic dependencies in a code base that hasn't been touched for the last 2 years, because then it's stable and then doesn't need to be done anything. But if you have code that is actively changed and very complex, then this is where you should focus your improvements. And the first thing would be to basically find out if you can reduce package cycles. Package cycles are worse than component cycles. And then if you have those big compilation unit cycles, also try to make them smaller. Breaking them up into smaller cycles is already a good gain. And we have some tutorial videos on our website that explains this process. I see I'm running out of time. We're almost at the end. I have to go a little faster here. Having an architectural model is always good. And once you have an architectural model, you can track your progress and see, by just looking at the metric, you can see if things are moving into the right direction or not. There's some source code management metrics that are really interesting. Basically, metrics derived from a version control system, change frequency, how many file changes did we have, how many commits, how many lines have been changed, what is the code churn rate, the lines that have been changed in relation to the total number of lines in your code base, and how many different authors have worked on a piece of code. And that can, at the end, lead to this hotspot map here. That's a three-dimensional visualization of a code base. Each of those little blocks is a building, a source file. The ground area of the block of the building is proportional to the lines of code, and the color and height of the building are assigned some arbitrary metrics. In that case, we have assigned complexity to the color, and height is the change frequency. So what we're looking for would be red skyscrapers. That's basically is based on Apache Cassandra. We don't have a red skyscraper, but we have a pretty big dark red building. That's basically the core class of Apache Cassandra that is changed frequently and medium complex and pretty big. So that is something where you may be focusing refactoring on. Okay, so